Hello class, today I want to go through 3 exercises in Practice It for binary tree programming. And the problem is, well, let's start just do one at a time. So this is exercise 17.3 depthSum. And so what is this thing going to do? So depthSum is going to return the sum of the values stored in the binary tree. That's simple, but it's weighted by the depth of each value. Now, actually, maybe I should start with just doing the depth, the sum of all the items in the tree, and then we can go by the depth. Okay, so this is not going to work. It's not going to think this is right, but I'll just show you just to start as a simple example. So we're going to be giving a public int, and what do they call it? depthSum. Now this is a method. All right, this is a method in the int tree class. So we have a this.overall root. Okay. So what we're going to do is depthSum is going to need to have a base case. So the base case, when we navigate down this tree, when we're down to the very end, what's the simplest problem here is when you have the last node. Actually, the last node, the very simplest problem is when you've got the left and right children of this, where it's null, and then you're just going to return the value 0. Okay, so that's the very simplest case. So base case, for null. Otherwise, we're going to have a recursive case. So when we have a recursive case, that's when we have, well, we can simply start at the top. So when we have a recursive case, we're going to need to add the value of this, which for an int tree node is going to be the this.data. Okay, we're going to add this plus whatever, I can't really show you just the left-hand side, but whatever is in the left-hand side. So this, and then we have to add in whatever's in the right-hand side. So this. Okay, and so again, this is not what this problem is asking for, but we're going to have to return the value of this node plus values of left tree plus value of right tree. Okay, and if the left tree or right tree are null, then it just defaults to this base case. So the base case, if this oh, you know, yeah, we need to, I was thinking we wouldn't need to do the helper method, but we are going to need to do the helper method. So let's add the helper method in. It's because we're going to have to at least pass what the subtree is. Public int depthSum, and then this just has to return depthSum of this.overall root. Okay, and so in case you haven't seen this before, we oftentimes, pretty much always, need a helper function because we are going to be calling recursively, and we have to know what part of the tree. So the first time it's called, this.overall root refers to the entire tree. But then the next recursive call, we just want to refer to this part of the tree. So we need to know where the start is, okay? And so we have to have something to tell us where the start was. It could actually be like some way of identifying what this node is, but it's simpler just to take this as the root node, okay? So we're just going to pass in the int tree node root. So if root equals null, return 0. Okay, the recursive case, otherwise, return this.data plus depthSum of root.left plus depthSum of root.right. Okay, let's try running this. Again, this is not going to work. It's going to complain, but we can at least see. Okay, I just need to put in return depthSum. Oh, we're up here. This is going to show us what? Okay, variable data. This dot data. Oh, it's root. Okay, so as expected, it didn't work. But what I want to see is what is the value of this tree? So 9 plus, let's do this. 6 plus 4 is 10. 9 plus 2 is 11, so that's 21. Plus 20 plus 5 is 26, 31, 38. So yes, that is correct value, 38. Here the value is 3, 5, 8, 9, 11, 15, 21, so that's correct. I don't bother to check all these, but that works. Okay, now the actual problem here is it's weighted by the depth of each value. So it's going to be 9 plus 2 times 7 plus 2 times 6 plus 3 times, etc., etc. So we now need another variable passed around besides the overall root. We now need to take a depth. Okay, so the first thing we need to know is what's the depth of the overall root. So by their definition, it is 1 because it's going to be 1 times 9. Okay, and then it's going to be 2 times 7. Okay, there it is. 2 times 7 plus 6. 3 times 3, 2, 4, etc. Okay, so that's the first thing. When it's called the first time, the depth has to be 1. And then second of all, where do we use depth? Okay, so that's going to be here. Some people initially, it's easy to get confused and think you need to do the depth times the root, the left and the right. But what happens for the left and the right is we actually pass in a new depth. Depth plus 1. Okay, so that's how we get 2 times these, 3 times these, 4 times these. All right, so let's submit. All right, so what did you learn here? Number one, we learned how you need helpers. Okay, in order to do these recursive calls, you have to be able to recursively pass down where you're at. And since this is in a class, the only thing we really have is this. So to replace the this.overall root, we need to take a new parameter. The second thing is that in many cases, we'll need a second parameter, a third parameter, whatever, multiple parameters. In this case, it's a depth, okay? And we know that in all recursive code, we need a base case, which is going to be the simplest case you can answer, and then we need a recursive case. And this recursive case is, in this case, since we're getting values, we had to deal with the value here, and then we just looked recursively for the values on the left and the right. All right, let's figure out what's our next problem. The next problem is exercise 17.4, countEvenBranches. So write a method, countEvenBranches. I'm going to go ahead and copy that returns the number of branch nodes in a binary tree that contain even numbers. So that's going to be here, here. Okay, and there's a branch node is one that has 1 or 2 children, not a leaf node. So this is a leaf node. This is a leaf node. This is a leaf node. So not those two, but we've got 2, 8, and 6. It returns 3 because they're, again, 2, 8, and 6. Okay. So maybe we could do this again in 2 phases. The first phase, let's just go do the whole tree. Okay, adding up the even branches, and then we'll figure out how to remove the leaves. Okay, so similar to before, we've got public, and then it's going to be an int since we're counting, and the first one is going to call countEvenBranches. Again, it's a helper, so we're going to pass in the this.overall root. Okay, I may need to add another argument, but let's just start there. And then second real function is now going to take a int node root. All right. So what we need to do is to return the even numbered items. So recursive base case for, again, let's see. Yeah, it's going to be null. We're going to return 0. So the recursive case. So we need to return, it's similar to before. So we're going to return the value of this branch plus left branch plus right branch. Okay, and again, we're not going to do quite the way they want. We're not going to exclude leaves right now. We're just going to do it for everything. Okay, so again, if the root equals null, return 0. The recursive case, so we're going to return what is the value of this branch. Now we are going to check whether it's even or not, though, because yeah, we're just going to do if root.data mod2 equals 0. So if it is even, then return that's going to be the root.data, or sorry, it's that we're doing the count. So it's going to be 1 plus countEvenBranches. Copy and paste that of the root.left, countEvenBranches of the root.right. All right, so we're going to ignore whether it works correctly for leaves, and we're just going to, so if, oh, okay, so, but we need to also do it if it's not even, because we still need to do this. So if it's not even, so here it's even, so we want to add 1 plus whatever is here and plus whatever is here. But in the case here, for example, where it's odd, we don't want to add, we don't want to just return nothing. We still need to add 0 for this, but then we still need to go down the left and the right. Okay, so that's why I have an else. Okay, so and we need to just replace that with 0. Let's just get rid of that, right? So it's still going to go down the left and the right trees. And I think, all right, so it failed, which I knew it was going to fail, but let's see what the error was. So my output was 5, and again, so I'm ignoring whether it's a leaf or not. So it was 1, 2, 3, but also 0 and 4 would make it 5. In this case here, there's going to be 1, 2, 3. So yes, so it's working, okay, but we're not excluding leaves. So now let's figure out how to exclude leaves. So we want to exclude it. So this is basically the exclude case, right? So we want to exclude it if the item is even, or sorry, odd, or so what I could do is here is I could write something here, but I'm going to write it up here because it'll just make it simpler. So if it's 0, I also want to exclude it if the left and right tree are null. If the left and right tree are null. So I have to but I need to invert the logic of that because I'm putting it in the opposite case. So if that and tree.left actually let's do this. Tree.left, we want to include it if the tree.left doesn't equal null or the tree.right doesn't equal null. I'm having to invert my logic here, so I'll explain it in just a second. So what this is going to say, include it if the value is even and not a leaf. Okay, so how did I figure out it's not a leaf? It's not a leaf if either the left or right exists. So that's how not a leaf translates. All right, so we're going to include it. So now let's try running it. Not quite. Oh, I just had an error. And, oh, instead of tree, I need root. Okay, so that works in all cases. All right, so what did we learn here? Well, a lot of this is the same from the last time. We have a helper function that passes in the this.overall root. We had the base case. What is new here is that we had a fairly complex set of rules, and we had to do two different executions depending on whether it met the criteria or not. So just a little slight difference, but it was a lot the same. The next problem is going to be fairly different. So I'm going to switch over to that. Okay, so this is exercise 17.12 to remove leaves, and it builds on the one we just covered because we just covered one that had to do with leaves. So we just wrote some code that will detect whether something is a leaf. It has no children, okay? So here's a leaf, here's a leaf, here's a leaf, here's a leaf. So this is going to remove all of those leaves. It's going to cut this one, this one, this one, and this one off. So it's going to be somewhat similar to the last problem, in that we have to cut off the leaves, but with one important difference, which I will actually cover last. So let's go into the code and again write some similar code. Let's get this function name here. So we're going to need public. It's no longer an int. Now it's a void. No, it's actually an int tree. Well, here, let's try it this way. Let's try public void remove leaves because we're not summing up anything. It's actually not right. I'll explain later why. But let's just try doing it without that. Let me put that down there. So public remove leaves. This is going to call remove leaves this dot overall root. So again, this is very similar to the way we did it before, and this is going to be int tree node of root. Okay, and then let's figure out what code we need here. So we know we're going to need a base case and a recursive case. So what's our base case? As you might imagine, it's always been the case before. If it's null, then, well, I'm not going to say return anything, then we're done, right? And the recursive case, otherwise, if it's a recursive case, so if we have children, then what we're going to need to do is to call it on the left and right. Okay, so let's try doing this. Let's say if root equals null, return. And otherwise, recursive case, so we need to call it on, let's just try doing remove leaves on the root dot left, remove leaves on the root dot right. And this seems deceptively simple, right? We're actually not doing anything. So we need another case here. We actually need a case where if it's a if leaf, then remove it. Okay, so how do we check if it's a leaf? If the root dot left, so we can't check it at the level where root is already null because that's too late. So let's take a look up here. By the way, I don't really like the way they do this. This is the sample problem they're going to call it on. But then what they did is they called it a second time and a third time. So ignore those, all right? This sample, what it should have shown is that removing this, 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 and this. All right, but when we get down to here where it's null, all right, Here it's too late. We need to catch this when we're up here, and we can actually see that the roots left and right are null. And that's why we're gonna, normally we would not try to look ahead for recursion, but in this case we have to, it's our only choice. So if root.left equals null and root.right equals null, okay, so now we need to remove it. How do we remove it? Let's think about that. So how are we going to cause this root to be removed? We need to actually we need to figure out some way so that when this guy calls removeLeaves on this, it's going to be gone, right? So let's try setting root to null. Okay, let's just try that and see what happens. I'll give you a hint, this is not going to work. And let's see, okay, well, first of all, we got a null pointer exception. Where is that? That didn't help very much, but I'll tell you what went wrong, okay? So what I think is happening here is, let's see, where did it? It's going to call it on this overall root, if not root null, return. If root and left and right, no. So it's going to first recurse down here. And that first time when it gets all the way down to here, that's where it's going to return null from calling the removeLeaves left and right on one. So when it calls root.left, that's a null, right? So it passes in null. So it returns, and then it calls it on the right, and then it returns, and then it's going to go back up to, so it called left. It's going to return. It's kind of hard to explain what went wrong, but let me tell you what went wrong. I just figured out what went wrong and how to explain it. So, looking up a level above where I was pointing at you, what it does is it says if the root left and right are null, then the root is null. So then it's going to try to operate on the null pointer. Okay, so let's try to fix this, which again is not correct, but let's try fixing it. If root doesn't equal null, or let's just do an else, right? So this will do it if it's not null. Let's try fixing that there. They should at least not crash. All right, so it didn't crash. So here's what it starts out before. Here's what they expected, and here's what happened. No change happened. So you notice this is exactly the same as this up here. So why is that? The reason why this is if you read the chapter, you notice there was a section at the end where it says x equals change x. And that's the problem here. Sometimes you have problems where what you're trying to do is you're actually trying to change what the tree looks like. Okay? In the lowest level here, when this guy returns here, by setting root equals null, we did not change what this guy's root.left pointed to. In order to do that, we actually have to change what root.left points to here. Let me try to show you in the code. Okay, so down here, we tried to set the root to null. Okay, but notice, first of all, we're not returning root. Okay, so there's no way it could affect the caller. But even more so, here, this is not changing anything. So this is where the x equals change x solution comes in. What we need to do is actually set this dot overall root equals removeLeaves. Okay, so this is where the x equals change x comes in. Only by changing this guy's root can we affect what the tree actually points to. So anytime you have a binary tree recursion problem that actually is trying to change not just the values, but actually change what the tree looks like in terms of structure, you need to use x equals change x. Okay, so in here, instead of returning void, we now need to return an int tree. And do we need to? I'm not sure. So sure this actually has to be return an int tree or not, because this is only called once. So as long as we actually do set the overall root, we should be fine. So we're going to be returning int tree, and so now it's no longer return null. I mean, we actually have to put in return null. And then here, if the left and right children are null, we actually have to return null. Otherwise, we can't just call these. We need to, again, do root.left equals and root.right equals. Okay, so now it's actually using x equals change x. And I referred to the wrong name in, I can't find class int tree. Oh, I just misspelled int tree. Right there. Okay, still an error. And data types, this.overall root equals removeLeaves, this.overall root. Okay, so it's a mismatch int tree node. Sorry, int tree node. And I need a missing return statement here. Yes, do need that. We need to return the root. Okay, that's got to change. Okay, so I'm actually, after all that work, it works. So let's talk more about how this works. Okay, so what did we learn here? Number one, we learned x equals change x. Okay, I'm going to write that down so that you can look it up. X equals change x. Sometimes when you have a function that's actually trying to change the structure, you actually have to do this. Okay, you actually need to take the result of the function and then replace the tree itself. Okay, so we're using x equals change x. That's number one. Number two is you can actually not just use the root.left and the root.right in recursion, you can actually set what they are. So again, when you want to change the structure, you need to do x equals change x. Okay, so here we're actually setting what the root left is and setting what the right is. And let's take a look at an example of where does that change happen. So here in this first execution, when this guy calls the root.left equals removeLeaves of root of this root.left here, it's going to get back null, and that line we just looked at is what's happening right here. It's going to trim it off and have it be null. So when you do the x equals change x, don't forget you need to return. Okay, so before we just had voids, but now we're going to have to return something at every step of the way. Okay. All right, so that really is a good overall picture of how binary tree programming problems work. Binary tree programming problems are always recursive. That's the nature of binary trees, so it only makes sense to do it recursively. Recursion means that we're going to need to use a helper function because we want to first start on this overall tree, then we're going to want to work on this subtree, then we're going to want to work on this subtree, then we're going to want to work on this null subtree. Okay, so we need a helper function to pass that down at each point. In this particular case, we didn't actually need to pass a second parameter like we did in the previous problem where it was a depth, or 2 problems ago was a depth. What was it last problem? I don't think we actually needed something in the last problem. But sometimes you do, sometimes you don't. Okay, and but in this particular problem, the big things is that you learn how to use x equals change x and how to actually replace the root left and right. Okay, so hopefully that gives you a good overview of binary tree programming problems. And there's a lot of other great problems in here I would suggest you do. And that'll be an excellent preparation for for knowing anything you need to know about binary tree programming.